The study of extreme events in dynamical systems is crucial for understanding and predicting rare, high-impact phenomena in various fields. The authors investigate the emergence of extreme rotational events in a forced-damped nonlinear pendulum under the influence of DC and AC torque. The pendulum's angular velocity occasionally exhibits large amplitude events that deviate significantly from a well-defined threshold, with a probability distribution supported by exponential statistics. The research focuses on the rotational dynamics of the pendulum, which exhibits libration and rotation motions. The authors identify a range of pendulum lengths for which the angular velocity displays intermittent extreme rotational events, characterized by a sudden increase in the size of the chaotic attractor due to interior crisis. This crisis is responsible for triggering large amplitude events in the system. The numerical results show a phase slip during the transition from libration to rotation, with a large phase slip observed during the appearance of extreme rotational events. The return interval distributions of these events are found to be exponential. The study offers valuable insights into the emergence of extreme rotational events in dynamical systems, which may have implications for understanding continuous time systems with strange attractors. The authors use a forced damped nonlinear pendulum model, governed by the equation ml² plus gq equals mgl sin q plus t sin wt plus f, where q is the phase variable, and q and diaresis q denote the angular velocity and angular acceleration, respectively. The parameters are chosen to be m equals 1.0, g equals 1.0, gamma equals 0.75, t equals 0.4, t equals 0.7167, W equals 0.25, and F equals 22/7. The study's significance lies in its ability to shed light on the origin of extreme events in dynamical systems, which can be applied to various fields, including natural and human-made disasters. The research provides a deeper understanding of the underlying mechanisms driving extreme events, which is crucial for developing strategies for prediction and mitigation. The paper discusses the emergence of extreme rotational events, ArXiv, in a forced damped nonlinear pendulum model, examining the impact of varying pendulum length, L, as a bifurcation parameter. The system exhibits periodic dynamics at first, transitioning to chaotic oscillations via period doubling bifurcation after a certain value of L. It then transitions back to periodic oscillation through inverse period doubling bifurcation. The authors identified two types of motion, librational and rotational, with a threshold of 0.5 for Qmax to distinguish between them. They also define ArXiv as rotational events exceeding a specific threshold, Ht, which is determined by the mean and standard deviation of a dataset of rotational events. In the bifurcation diagram, a sudden transition from chaotic oscillation to large amplitude chaotic oscillation occurs at a critical value, L, indicating an interior crisis. Similarly, another crisis occurs at R when decreasing L, leading to a transition from small amplitude chaotic libration to large amplitude chaotic libration and rotation. The diagram also shows that the chaotic attractor expands during these crises, and intermittent excursions occur in the post-crisis attractor, resulting in ArXiv. The temporal dynamics and corresponding phase spaces are presented for 5 different values of L. For L equals 0.999941, no large spikes or bursts are observed, and the trajectory bounds within a small portion of the cylindrical phase space. At L equals 0.999945, occasional large spikes appear, indicating the presence of ArXiv, with the trajectory occasionally traveling far away from its bounded region in the phase space. At L equals 1.001, ArXiv disappear, and the trajectory remains within a bounded region in the phase space. However, for L equals 1.00218, intermittent large spikes reappear, and a few rotational events exceed the threshold, Ht, qualifying as ArXiv. The phase space shows the trajectory evolving within a portion of the cylindrical surface. The study concludes that the intravent intervals between ArXiv follow an exponential distribution, while their amplitudes exhibit a non-Gaussian distribution. The choice of d in the threshold, Ht, is crucial for characterizing ArXiv, as it determines how far the deviation is from the mean state. The paper highlights the importance of understanding the emergence of errors in complex systems, particularly in the context of forced-damped nonlinear pendulums, and demonstrates the role of interior crises in generating these events. The research paper explores the emergence of extreme rotational events, ER, in a pendulum system, which is driven by a periodic torque. It highlights that these errors are generated through an interior crisis, a sudden and qualitative change in the chaotic attractor. The bifurcation diagram in Fig. 3 reveals 5 distinct regimes for pendulum lengths L between 0.998 and 1.004. Before the pre-crisis regime, where L less than 0.999942, no errors are observed. However, as the pendulum length crosses the critical value of L equals 0.999942, a sudden expansion of the chaotic attractor occurs, leading to the appearance of errors. To validate this claim, the authors gather sufficient data and plot histograms for different pendulum lengths. For L equals 0.999941, the data related to rotational and librational motions are clearly separated, with no data crossing the threshold HT, indicating no errors. Conversely, for L equals 0.999945, a significant portion of the data crosses the red line, confirming the presence of errors. This finding supports the bifurcation analysis provided in Fig. 3. The shaded box in the bifurcation diagram indicates the region where errors can be anticipated. The temporal dynamics and corresponding phase spaces are depicted in Fig. 4, showing the absence of errors before the crisis point L, and their appearance after the crisis point L and R. The phase difference plot in Fig. 5 demonstrates phase slips during the transition between libration and rotation, which is a characteristic of errors. The statistics of errors are further analyzed in Fig. 6, where the histograms for L equals 0.999941, 0.999945, and 1.001 show distinct distributions of rotational and librational motions, with errors observed only after the crisis point L. The paper concludes that the emergence of errors is linked to interior crises, which cause sudden and qualitative changes in the chaotic attractor, leading to intermittent large spikes in the time series of Q. The study investigates the emergence of extreme rotational events, errors, in a forced-damped nonlinear pendulum under the influence of AC and DC torque. The researchers analyzed the librational and rotational dynamics using bifurcation analysis, which helps detect the emergence of EREs in the rotational dynamics. The system exhibits rotational and librational dynamics, with occasional high-amplitude rotational events. The researchers collect data on the rotational and librational motion over long iterations, discarding a transient of length 10 to the power of 6. They plot histograms of the data in semilog scale, showing 2 distinct groups corresponding to librational and rotational motion. The gap between the groups is due to the presence of 2 different motions. The researchers also plot the extreme rotational event qualifying threshold, which helps distinguish errors from chaotic rotational dynamics. The study further investigates the intravent intervals between errors, calculating the probability density functions, PDFs, of the intravent intervals in semilog scale. The numerical data fits well with the continuous exponential distribution, indicating that small intravent intervals have higher probabilities of occurrence of errors. The researchers calculate the rate parameter and coefficient of variation, CV, for the gathered data, confirming that the data is distributed according to the exponential distribution. The researchers conclude that the suitable choice of pendulum length can produce large amplitude rotational motion, and the system displays rotational and librational dynamics with occasional high-amplitude rotational events. They also suggest that the chaotic attractor in the rotational motion suddenly enlarges at 2 different post-crisis regimes due to the interior crisis, generating intermittent behavior in the rotational dynamics. The study highlights the importance of understanding the emergence of extreme events in nonlinear dynamical systems and encourages further research into the causes of these extreme rotational events in other non-equilibrium systems. The researchers also suggest investigating coupled nonlinear pendula and examining whether the observed signature of extreme rotational events is experimentally observable. The research paper under consideration presents a comprehensive review of the literature on complex systems, chaos theory, and synchronization. The authors provide an extensive list of references, showcasing the breadth of research in this field. The references cited span various disciplines, including physics, biology, mathematics, and engineering, highlighting the interdisciplinary nature of complex systems research. The authors draw from a wide range of sources, including journal articles, conference proceedings, and books, demonstrating their thoroughness in reviewing the existing literature. The references cover various topics, such as the theory of complex systems, chaos theory, synchronization, and nonlinear dynamics. The authors also explore the applications of these concepts in different fields, including geophysics, biology, and engineering. Some notable references include the work of Sornet et al. 1996, on the theory of complex systems, the research of Scheffer and Carpenter, 2003, on tipping points in complex systems, and the study of Krause et al. 2015, on the synchronization of complex networks. The authors also cite more recent studies, such as the work of Ray et al. 2020, on the synchronization of chaotic systems, and the research of Sudharsan et al. 2021, on the dynamics of complex networks. The extensive list of references provided by the authors demonstrates their commitment to thoroughness and accuracy in their research. The breadth of sources cited also highlights the complexity and richness of the field of complex systems research. The transition to page 10 of the paper reveals a continuation of the reference list, with citations from researchers such as Govindan et al. 2009, and Santhanam and Kantz, 2008. These references further reinforce the author's comprehensive review of the literature on complex systems and chaos theory.